Welcome to the shop. I'm going to be continuing NQALHA Production Run 4. Each NQALHA has 75 custom-made parts, and I'm making 10 units. So that's 750 parts. I better get going. In this video, I'm going to be trying something new. The toolpath that I used is a variant of a trusted toolpath. This toolpath kind of ran a little slow, and I'm always trying to increase my production rate while not sacrificing quality, obviously. I need to be making good parts. So I'm attempting something that I've never attempted before here, and we'll see how it comes out. I created two different tool paths for the two halves of the clamp body and the clamp cover. Now these parts are very similar. They mate together, and in their final operation they're actually screwed together on a tooling plate, and the outside profile is created with both parts together. And the outside profile is then milled on both parts. And so I thought, well, since the two parts are so similar, they use the same tools, and a tool change operation on the Tormach is really, really slow because of the very slow rapid feed and the very slow automatic tool changer. I tried, just in a text editor, combining and kind of intertwingling the tool paths so that I could put the clamp body in the right vise, the work offset 1 G54, put the clamp cover in the left vise, work offset 3 G56, with the Z0 set at the top of the part, and standard that I always do, left rear corner, and then with the intertwingled G-codes, hopefully minimize tool changes and be able to make two parts at one time. So this is going to be the first time I've ever tried this, and hopefully everything goes right, but hey, gotta be careful, gotta pay attention. And in yesterday's video, the GoPro just stopped recording for some odd reason. I have no idea why it misbehaves like this, but I'm going to try to pay attention to its little blinking light to make sure that it still is on the job. And wow, you take something that requires concentration like glasswork or CNC machining, and then make it more difficult by trying to do a video. Oh. So let's start off. Standard operating procedure. Single block mode. Verifying that the pre-feed height of 1 inch above the part is correct, verifying that it looks like it's roughly in a reasonable, sane position. Of course, these pieces of the tool path that I mixed together by hand, the pieces themselves are more or less known and trusted and tested, although, hey, start dicking with stuff and all bets are off. (2500 RPM, 10 inches per minute, fast peck at 150 thousandths per peck. Okay, now let's see if the first intertwingle works. That, it kind of does work, but okay, that's correct. The Z-axis the go to the z-axis clear, that went up way too high. So here's another opportunity for optimization. I'm also going to probably change that PEC cycle a little bit. I got more buildup, more of a rat nest on the tool, and I really don't like that. So, and I can already tell that this is incorrect. So it's off to the CAD room. Okay, so here's what I learned. That, it's not really that I learned, I kind of remembered a little bit too late after doing it wrong and then catching it before it ruined my part. But here's what the problem was. G-codes are modal, and that means that once a work offset has been set, the system assumes that, well, it's going to retain that work offset until changed. So when I manually intertwingled the operations sorted by tool number, I didn't manually insert the work offset specifically. And so since it had just finished an operation on work offset 3, it didn't know to go back to work offset 1 because the original tool path, it would have been followed by another operation in work offset 3. So let's try that one again. And going to be just air drilling those holes. I'm probably going to change the feed parameters, and it really didn't need to do a spindle stop there. Ah, the joys of manual G-code editing. Of course, there's always a trade-off here that, let me make sure this works before I start talking too much. Okay, over to the correct work offset. Pre-feed looks correct. Feed looks correct. Going to be roughing out a slot here using the aluminum shredder roughing cutter. This slot is a fairly critical slot because this is where the clamp bar slides, and it's got to be pretty accurate. One of the challenges that I face in this project is that, and that is looking pretty good, one of the challenges that I face in this project is that the clamp bar is made from cold rolled steel, and the cold rolled steel is, let me stop talking and pay attention for a moment. And that, I really don't like that. I really don't like that at all. So this is turning out to be substantially more difficult than I thought, and I'm kind of going crazy trying to debug the toolpath at the same time that I'm talking about my part. The clamp bar on the NQALHA is made of cold rolled steel, and cold rolled steel is made to reasonably good tolerance, but it's not great, and I kind of wish I had a surface grinder. What I do now is I just kind of inspect the piece to see that it's within tolerance, and if it isn't, I go find a piece that is. I might actually try running the piece, either putting it on the mill and skinning the surface, or try putting it through my woodworking drum sander, and who knows, maybe someday I'll actually buy a surface grinder. Then the problem gets worse because the part gets plated. And so I need to provide sufficient slop to tolerate the manufacturing tolerance plus the plating tolerance, while still making the clamp slide smoothly on the clamp bar, but not so smoothly that it slops around and flops around and doesn't clamp properly. So this part is a bit of a trick, trying to get it to come out right. And anyway, back to the CAD room. Depending on how long this troubleshooting process takes, I may just stop the video and restart after everything is working, but I think you can probably see that for someone who depends on a toolpath generator, yeah, that worked correctly. For someone that depends on a toolpath generator and doesn't do a whole lot of manual G-code, this process is a little bit more troublesome than I expected it would be, so let's find out. Of course, there's also always the question, am I going to consume 3 or 4 hours troubleshooting and debugging an optimized toolpath in order to save an hour of cycle time? So strictly speaking, if all I was talking about is getting the job done faster, the answer is probably no. It's probably not worth it. But, you know, part of the reason I do this is just the challenge of, well, how good can I do it? How good can I make it? And so even if it does take longer to create this optimized toolpath, it's kind of a fun challenge. Okay, now after, boy, you know, what happens if you're not paying attention? After wasting all that time and going off on that big old rant, thinking, oh, there's something wrong. No, there's not. That's actually the way it was programmed. Now, I might ask myself, is it programmed correctly? was that actually what I wanted, but yeah, that's the way I programmed it. So I'm cutting a slot with a 1/4 inch 3-flute carbide zirconium nitride coated end mill, and cutting fairly slowly. I could probably speed up the feed rate a little bit, but I've had trouble with cutting slots with 1/4 inch end mills that, you know, I've had chip evacuation problem and cutter breakage problems, and so I think I was being a little bit extra conservative on this one, and 10 inches per minute is probably absurdly conservative, so I may go and bump it up a little bit. So except for the very conservative feed rate, it's actually looking correct here. This is a somewhat complicated part. This is the part that houses the cam and the clamping mechanism along with a couple of springs. And it's a slightly challenging part to make and get right. The previous tool path was even slower and more conservative, so little bit by little bit as I make these parts, they get a little more efficient to make. So now comes the really scary part with an 1/8 inch end mill. Now, pre-feed looks correct. There's a slot in the part where a little compression spring is inserted, and the 1/4 inch end mill produces a 1/4 inch radius, and I want the end of the compression spring to sit flat against a flat surface, but also be constrained side by side by flat sides. Ideally, I would prefer a sharp corner so that I'd have a flat surface and sharp sides, but the compromise that I make is to put a little bit of a kind of a T at the top of the slot using an 1/8 inch end mill. And boy, oh boy, you gotta be careful on CNC with an 1/8 inch end mill, so wish me luck. Slow feed in Z. Looks to be good. Didn't break the cutter. Got that spindle stop again, which is not something that I like. Looks like that was completed successfully. So now, going to drill some clearance holes. Verify pre-feed correct, verify feed correct. Fast peck cycle, 5140 RPM, 10 inches per minute, 60 thousandths per peck. and it looks like it's operating correctly. And I might change that peck. I'm getting a little more buildup there than I would like. And that is not correct. As I was cutting and pasting my intertwinglement, I left in the M30, which is program end, before finishing the last part. So back to the CAD room. I just made a made a quick modified toolpath so I don't have to go through that whole thing cutting air. I think things are looking pretty good. Single block mode, verify pre-feed, verify feed, peck drill, fast peck, looking good. And that one looks, the drill is coming out much cleaner than it did before. So I believe that all is going to be well. Check out the tap. Once again, I put manually in the post processor, inserted an M0 pause because flood coolant doesn't work well with the Tormach compression tension tapping head. First of all, it just hits the body, it doesn't get on the tap. And second of all, it doesn't really work that good. I use Tap Magic for aluminum, which is an excellent tapping fluid. It really is magic. And I carefully blow off, even though the spiral flute tap ejects the chips up out of the hole, I still carefully with the air nozzle so I don't blow the chips back into the hole. I do blow them off. So what I'm going to do now, this part is a somewhat critical part, and I kind of don't like that. I think I'm gonna, I don't know, maybe yes, maybe no. What I'm looking at here, I've got a bit of a burr because I cut the deep slot first and then cut the deep slot first, then cut the shallow slot, and so that results in a bit of a burr here. That will probably go away in the vibratory polisher, but I'm not sure I like that. I may go back and, of course, if I don't stop myself, I'm just gonna keep dicking with this tool path all day and never get any parts made. So one thing I am going to do after some hand deburring, I'm going to do a bit of a sanity check here before I make a whole batch of bad parts. I go, do a test fit. Yep, fits fine. So, I'm going to do a couple of more optimizations over in the CAD room, and then come back and run some parts. This video, I'm not really sure how useful it is, but there's a chance that it might be very useful, because there's a misconception among, I think, people who don't do CNC machining about how easy CNC machining is, that, oh, it doesn't take any skill, all you do is push the button and the machine does all the work. Well, if you're I mean, that may be true if you're just a button pusher and somebody else has done the setup and somebody else has done the tool path and somebody else has verified the program. Yeah, you can probably have an untrained person just load, part, push button, but generating a tool path, optimizing a tool path, perfecting a tool path, testing a tool path, and making sure not to crash the machine and ruin parts while you're doing it, you know, that's not trivial. So maybe, possibly for people who, you know, are curious about the process, seeing me fumble through all of these steps might actually be educational. So, gonna cut another 2 blanks, and the long material that I use kind of has to go out the back door, and I did set up the shop that way, where all of my chop saws are in line with the back doors. Of course, it has one slightly annoying side effect that bugs me a bit. Now I've got nasty ass backlighting on my video. And no, it's not worth cutting a hole in the garage door or putting up some sort of weird shield just for lighting. Hey, I can live with it. So, with any luck, I actually edited the G-code correctly and didn't booger anything up. And with any luck, I should be ready to go. So here goes. See if this thing is going to be a little less insane. Always got the finger on the stop button. Nope. One more change to make. once again, I'm using the aluminum shredder, roughing tool, 3 flute solid carbide serrated flute, and the aluminum shredder makes very, very small chips that are evacuated from the cut very efficiently by the flood coolant. So this is looking reasonably sane. That M998 that I left in was a very minor annoyance that I'll be removing as I continue to perfect this tool path, but things are actually looking quite nice. There's an optimization that if I really, really wanted to avoid, if I really wanted to save another second or two, there's another optimization I could make, but I don't want to drive myself crazy with optimizations. I could be here all day, be here all week, dicking around with optimizations. Nope, didn't get that one right. Feed rate's still at 10. So I think I've probably shown enough of this. I'm probably just going to stop the video and continue optimizing until I decide that I don't need to optimize anymore, and then come back and restart the video again for the second and third operations, which will be milling the profile and then tapping some holes in the edge of the part perpendicular to the milled surface. So, see you later. So, I changed my mind. I am going to show the tool path operating at full speed after all the optimization that I care to do. There's still a few more optimizations that I could do, but I'm not going to drive myself crazy. I've already spent much more time in toolpath optimization than I would have spent using the old trusted toolpaths. It was an interesting adventure figuring out how to do this and getting a little bit of experience hand editing G-code. It's not the first time I've done it, but I don't do it very often. So here goes, full speed, the semi-optimized toolpath. .2500 RPM, 10 inches per minute, fast peck, and I believe it's about 150 per peck. Now here comes one of the optimizations that if I really cared, I could get rid of that little Z bounce, but I'm not going to drive myself crazy. Well, maybe I already am crazy, so how much more can I get? How much crazier could I get? Trying to minimize tool changes and also minimize the number of shifts back and forth between work offset 1 and work offset 3. Here's the roughing cutter, 3-flute, solid carbide, the aluminum shredder by Lakeshore Carbide, 5140 RPM, 40 inches per minute, running a pocketing cycle, leaving a little bit both in the X, the Y, and the Z for the finishing cutter to finish up. This slot is one of the more critical parts in the design, which is one of the reasons why I'm indexing off the top of the part, because the distance from the top of the part to the depth of the groove is the critical distance. And like I said before, this part needs to have a nice sliding fit without too much slop on a piece of 1/8 inch thick by 3/4 cold rolled steel, which is then plated. So I have several different tolerances that I need to be concerned with. The material tolerance from the mill, the plating thickness, and the machining tolerance. So now we're moving over. In order to get the sequence right, I need to end up with the tap cycle at the last cycle. In order to get the sequence right, I made what appears to be an unnecessary work offset shift, but once again, I'm not going to drive myself too crazy with this. Optimize one thing, de-optimize the other thing. I've increased the feed speed on this 1/4 inch slot to 20 inches per minute, and while still conservative, I'm somewhat concerned about braking cutters with a 1/4 inch slotting bit. It's still conservative, but it's a little bit less outrageously conservative than it used to be at 10 inches per minute. So everything is looking nice. 3-flute solid carbide, also from Lakeshore Carbide, zirconium nitride coated, 5140 RPM, full machine speed at 20 inches per minute with a 10 inch per minute Z-axis feed. It's not doing a finish pass, it's simply doing a roughing pass at 2 different levels because the surface finish is good enough, the accuracy is good enough, it just doesn't need it. So now, going over to the little guy, the 1/8 inch 2-flute solid carbide, and this one, I think this one's actually a Rushmore. 5 inches per minute Z feed, 5 inches per minute XY feed, being very careful to avoid breaking the little guy. It's just barely opening up the ends of the surface on which the spring will rest. Okay, switching to a drill bit. This is an 832 clearance hole. where I drill my clearance holes as tight as I can. The standard chart for drilling clearance holes recommends a larger hole, and I use a smaller hole because I'm doing precision drilling, and why have slop if you don't need it? 5140 RPM, full machine speed, 10 inches per minute plunge, fast peck cycle, 60 thousandths per peck. The tool is more or less clean. If I really wanted to keep dicking with it, I could probably modify a little bit more, but the tool is clean enough and it's fine. Using a tap drill, since my parts don't require the ultimate strength of the threaded hole, I'm using a slightly larger tap drill for 60% thread as opposed to 75% thread, which is what the tap drill chart usually recommends if you look up the tap drill for an 832 tap. So when I need the full strength, I use the smaller size tap drill, but in this case, it makes the part is strong enough and it gives me a little more confidence when power tapping that I'm not going to have a tap breakage problem. So, cycle start, Tap Magic cutting fluid applied to all the holes. Gonna blow off the chips a little bit. I'm not sure what would happen if I didn't do this. It's possible that the tap geometry would just clear itself just fine, but I always got a little nervous about power tapping. So that shows the cycle as optimized as I'm going to do it. So I'm going to turn off the camera for real this time, and see you later when I do the profile and the side drill. Okay, so all of the parts are complete. The first operation is complete for the clamp body and clamp cover. So now I'm going to be machining the outside profile of both pieces at the same time. I'm using this tooling plate that I made that has a couple of steel pins pressed into precise holes, and these pins are tall enough that it supports both parts. And then I'm going to be using a 1/2-inch socket screw with a little aluminum washer to protect the surface of the part from getting boogered up. So let's get this guy clamped in place. 0 for this part is, this is going to be work offset 1, 0 on the surface of the tooling plate. And going to take the two pieces. Got to remember which side is up. It's not written on the setup sheet. So, of course, when I was making the parts last time, I remembered everything. Now I come back and realize, wow, I didn't write that down. Little bit by little bit, the documentation gets better. So the bottom part goes on first, and of course, flipping it upside down would result in catastrophic failure. Let's see if it's possible. No, actually the fixture only works one way, so even if I didn't write it down, I'd still be okay. So let's get that guy in place. And once again, This is a known trusted tool path, no modification, no optimization. It should just work, but you know, gotta be careful. Gotta pay attention. Now, yes, I believe that's going to be okay, but I'm going to do one kind of sanity check here just to make sure, because I sure would hate to get in trouble at this point. I'm checking the stick out of the cutter to make sure that I don't have a conflict with that hold down bolt. It worked before, but you know, in between then and now, I put in a new cutter and just put it in kind of by eye and kind of roughly approximately where I thought it should be. So always good to double check, triple check, check the check again, check and more check. Everything looks good. Multiple passes. Once again, like I said before, the Tormach, because of tool holding limitations and rigidity limitations, as well as spindle horsepower limitations, the Tormach really can't take a honkin' big cut. And so I'm going here at about roughly 1/8 of an inch depth of cut for each one of my passes. 5140 RPM, 40 inches per minute. The 3-flute solid carbide aluminum shredder roughing tool. And gonna throw the old eyeball on it just to make sure that I didn't have a conflict, and yes, all is well. Got a happy part. And then the roughing pass comes up next. Checking my blinking light to make sure the pesky GoPro hasn't decided to go on vacation. Single step. Verify pre-feed. Verify feed. Throw the old eyeball on it. Throw the old eyeball on it, but that did not look like totally safe. I'm gonna turn the machine off, and yeah, it really was safe, but you know, you can't be too careful. So you can probably guess what it's going to look like next time I run it, because it'll run correctly, but just looking at it from the side with the coolant, I was a tiny bit concerned I might have a stick-out problem, but no. So all is well. I'm going to run these parts, and then the final operation, this inside corner is not what I want. I actually want a sharp inside corner, so when I turn the part over this way, I'm going to be finishing this size with an end mill, with a sharp cornered end mill, and then drill the perpendicular tapped holes. So that will be the fourth operation with the two parts fastened together. So I'm going to turn the camera off, and when I come back, we'll finish this sucker. Okay, back again. I've got the parts, and let me just show you what these parts look like. That guy, I can get it in focus here. That guy is a reasonably complex part, and then the one that mates with it is also reasonably complex. And the next step in the operation is going to be to square out these corners. The corners here were cut with a round cutter, and they have a round inside radius. And I did that because, hey, it's already in the machine, might as well just hog out the material, makes the corner finishing operation go faster at almost no overall cycle time penalty. But what I need to do is square out these corners and then drill and tap a couple of holes into the part. So I'm looking here to make sure that I have the correct orientation of the part. I've installed slightly taller jaws and set work offset 2, which is a special work offset with the Z0 on the surface of the vise and the X and Y0 set with the Heimer indicator at the left rear corner. And then the two pieces are screwed together and they go into the vise in that orientation. Now, there's a couple of things going on here. Numerous things going on here at the same time. Because the pieces are screwed together, I have to do the corner squaring operation on both of them. Well, it speeds up the cycle time. It also, because the pieces are now clamped together and the squaring will be done with the pieces in the same position in the vise. Therefore, I'm confident that the holes will be the correct dimension relative to the sides. And the part that fits in here pretty tight. I don't want a loose fit. It's not a press fit, but I don't want a lot of slop. And so by doing this, I don't need to be concerned about, oh, is there a chip in my stop when I'm putting a part in and taking it out and putting it in and re-indicating? Is there going to be a tolerance buildup? Because I'm cutting the reference surfaces and drilling the holes in the same machine setup, that pretty much guarantees the holes will be correct relative to these sides. So, once again, this is a known trusted toolpath, run many times, but hey, I'm going to treat it like it's new. Single block mode, hand on the stop button, verify that it stops at a sane distance, and looks like, yes, that is a reasonable position for it to be in. And it appears to have correctly cut the slot. Next operation will be a couple of blind holes. And, you know, I'm gonna do a little sanity check here. I might be in trouble. Gotta make sure that I have sufficient stick out. I believe that will be okay. But, you know, it's always a concern when doing something like this, and I'm going to be very vigilant when I watch it to make sure. So since I stopped the tool path, I have to run it again. I'll probably edit that part out. I'm going to be very vigilant while this is going on. Single block mode, finger on the stop, eyeball at the ready. And, boy, that one was close. I probably could have used a fraction more stick out, but you know what they say, clearance is clearance, Clarence. So, next operation, 832 blind tapping, single block mode, verify somewhat sane. Now what I do, as you've seen before, I use Tap Magic for aluminum, but when I'm doing blind holes, I waste a little of the cutting fluid. I just fill the hole, fill it down to the bottom. That actually provides a little bit of hydrostatic pressure to push the chips out. And I really haven't had tap breakage problems, unless I make a mistake. Yes, I've done some stupid stuff and broken taps, but when the tool path is correct and the Tap Magic is applied, I haven't had a broken tap yet. Even my little 440s tap successfully. So this completes the machining operation on this part. Next step will be to take it over to the vibratory finisher. And no, I'm not going to show that on video because I tried showing it once and the thing is so loud you just about can't hear me yakking. And it's pretty boring. It's an El Cheapo Harbor Freight vibratory polisher. Works good enough. That's it for today. Thanks for watching.